Okay, so hi again, and welcome to our next talk in the Engineering Digital Twins community. Yeah, you probably know us already. You know the steering and organizing committee. So before we start with today's talk, let me briefly tell you that we have planned already some future talks with Andrea Matta, Jacqueline Lemoine, and Bentley Oaks, and they will be happening in March, April, and May, always on the second Monday of the month. And for today, we will have Andreas Gerndt, Professor Andreas Gerndt with us, who is head of the Visual Computing and Engineering Department at the German Aerospace Center, the DLR, but has also had a lot of other stops in his life already, from Fraunhofer to Aachen to the US. And in his work, currently, he focuses on the interactive visualization of very large scientific data sets, high performance computing, and, which is probably most interesting for us, model-based and model-driven systems engineering for space systems. And today, Andreas will talk about the engineering of the metaverse and how conceptual digital twins will be an enabler of this metaverse. So with that being said, I'm looking forward to your talk, Andreas, and I will leave the floor up to you.
Okay, thank you for your introduction. And I have to emphasize that I will not talk about metaverse as you might expect what metaverse is. We try to take the ideas behind metaverse for the engineering domain. There is some activities with Siemens and NVIDIA and so on industrial metaverse, but at DLR we are not so much in the industrial domain. We have an institute on robotics, and they have some projects on future factories and so on. But my goal in my department is the engineering, the systems engineering, and we think that metaverse, the concepts and ideas behind metaverse can also open some kind of doors for future engineering in systems engineering. And to think about the data we have to handle with, I think a digital twin could be definitely a good concept and therefore also an enabler to make it happen, to bring systems engineering in metaverse. Originally, my boss was invited to give a presentation. He's pretty well known in the community of system engineering, modeling, software engineering, more software engineering, I have to say. It is Michael Felder. He is the director of the Institute of Software Technology. We have, by the way, 4 different departments, and I'm a head of one of these departments, which is about visual computing and engineering. And here you can see 3 of the 3 groups of my department. And therefore, maybe you get already some ideas why I'm interested in the engineering metaverse, and why I want to combine that with system engineering, because the first group I have in my department is about modeling and simulation, so a pretty classical domain for that specific domain. And I have an extended reality group, so Georgia is on that, and the third group is on data visualization. And I like to bring all these activities together to have great synergy for systems engineering. All right, so I'm already at DLR for 15 years. And already for 15 years, we started with model-based systems engineering. Model-based is driven mainly by Incosi. Already at the moment, they publish their vision of modern systems engineering. It is published in the Vision 2035. It's available, so with that link you can get direct access to their ideas. And it's always, they are really at the leading edge with their ideas when it comes to future challenges of systems engineering. And at the moment, everybody knows that we have plenty of changes on a global scale. Those are the meta trends, as they call them, are related to environmental sustainability, Industry 4.5. So I do not know if this is still some future vision. I thought Industrial 5.0 might be already at the door, but it is related to connected world. So with that, a complete new challenge came into play also for systems engineering. So how can we exploit interconnected worlds? The digital transformation is a very important aspect. So as I started 15 years ago, I will show that I'm in a very specific systems engineering domain. There are some which are pretty at the leading edge. Other need much more time to get into some kind of transformation. But also digital transformation rocks the world of system engineering at the moment, and how the engineers work together. Yeah? The systems becomes more and more complex, becomes increasingly complex, so that the engineers have really create big problems to handle the complexity at all. The tools becomes more heterogeneous, so there is not just one tool or a suite of tools, but the tool landscape is pretty fragmented. Yeah, and then there's the big topics like big data. AI comes into play. On the right-hand side, you can see a screenshot of the INCOSE Vision 2035 and some of the technology advances. And one of them is what we follow already for decades. Let me say, this is the advanced modeling and simulation in virtual and augmented reality environments, yeah, to get a better understanding of the system. And here it is always the human. It is not the system. It is the human in the loop, which is of interest for us, for our development and our support we want to bring forward. But if I have all these heterogeneous, fragmented landscapes, very important to make systems engineering a success is that data can flow through all the instances and can be taken and processed by the next steps without any big obstacles. And therefore, data continuity becomes more and more important in that domain. Okay, so I've mentioned, so I'm already at DLR and working in this domain for 15 years. And INCOSE was always somehow our idea gave us some guidelines how we have to develop our systems so that we can support systems engineering. So they came already in 2007, they came up with the Systems Engineering Vision 2020. So I've mentioned, so the current one is a 2035 vision. In the Vision 2020, they said, okay, model-based systems engineering is a big topic, yeah, and we started with model-based systems engineering, and this was really a big success because we are at DLR, we are in the space domain. So my department is mainly supporting the systems engineers in the space domain, and space really needs time to incorporate new technologies. So it is clear, so if you want to plan a mission, you need maybe 20 years before the launch, and you cannot change all the time models or systems or subsystems. Yeah? So, and model-based system engineering was really the kickoff of a new approach. And nowadays, everybody talks about model-based system engineering. So that's the common tool, the common approach, also in the space domain. The big advantages of model-based system engineering, especially in the space domain, was that we addressed the gaps between all these different phases. So space is in Europe is specified, defined by the ECSS, that's the European Space Standard. And you can see between all these different phases, 0 to F, you have reviews in between, and you have some gaps, so that after the reviews, you have to create new data models and you have to start from scratch more or less. You have some requirements, you have documents, and documents is really important, not only for space, but also for aeronautics, also a big topic for DLR. So documents is really a mess, and therefore model-based system engineering came up with, you do not have to write documents. Documents comes from the models. So that was also a big step forward. The first big step was going through all the phases without these breaks, without these gaps, so that you have a continuous data usage through the phases, so you can grow up your models, and the models later on supports you to create the documents. Okay, that was the idea about 15 years ago. And now look at that, what the current status is. Actually, everybody is talking about model-based system engineering, but we have still the old problem. So we have the big players, the large systems integrators. So you know them. In Europe, it's Airbus. In Bremen, it is. There's also the headquarter of OHB, also a big player nowadays in the spacecraft domain. And we have just few organizations which offers the budget for the big systems. So it's either on the European level. Sometimes the money comes also from DLR, but not from the research part. I'm from the research part. We have also the DLR agency organizing missions, the space missions here for Germany, and the money goes then to the big players, so Airbus and OHB. So they can specify, they can define, request what they want to get from the subcontractors. So they have their own tools. They develop their own tool chains, and they are incompatible. So if you have a tool chain from Airbus, it does not work with OHB. Even if you want to exchange in between the phases, you have big issues with that. So they specify the requirements, they hand over the requirements to the subcontractors or to the developers of subsystems. So they have then their own tools to create something, then it goes to the suppliers, they offer their parts, and then it goes backwards through the pipeline, so that parts are delivered, and again compliance documents has to be issued, and then you can assemble a system, compliance documents has to be issued, and at the end you will get a big product. It is a satellite, and often it is a single unit production. You see, it is not really that what we had in mind with model-based systems engineering. Data flows through the life cycle, development life cycle. At the end, you get a document, a product, but everything is generated by models. This is not the case, unfortunately. Still a lot of documents, still a lot of tools. All right, so how can we overcome that, or what is the idea to leverage this game a little bit? And it is data interoperability. If we have so many different tools, at least the data should work with the different tools. And therefore, we need systems which can share, understand, and use the data created and processed, so that it goes seamlessly through all the development phases. So the interoperability is somehow divided in different aspects, so listed here. So we have, for instance, data repositories. So data repositories are some kind of rooms for collaboration. So data comes in, and now everybody can get hand on the data. So Gaia X was a nice approach by the European Commission to offer some kind of a cloud system for the European industry to exchange data. We had also a project, it's still running, we are almost done with that. It's called Cooperance, to exploit also this cloud-based approach, repository approach for data exchange and for spacecraft development. So the second corner is common data formats. In the space domain, we rely on SysML. So nowadays there's a version 2 available. We have to rely on ECSS. So there's no mission without ECSS. So we have to follow all the recommendations and requests by this European standard. But this is needed so that we speak the same language. So common data formats allows us to speak the same language. The third corner is about the API. So when it comes to software development, system engineering, the different tools has to speak with each other. So this happens with the via APIs, so application programming interfaces, and they have to be open. So JSON is a nice example depicted here, but all these exchange is useless if they have no meaning. So if the data cannot be understood by tools, they need some kind of semantics, and therefore ontologies is also a big topic in the space domain, so that we understand each other between the tools and the systems. All right, so we are pretty active in the early phases of the spacecraft development life cycle. It's the phase 0 and A, and here in general, the so-called concurrent engineering facility comes into play. A concurrent engineering facility is a quite interesting approach to reduce the development life cycle, to reduce the time to develop a system, and also to reduce the risk to create failure you detect later on in the life cycle. The idea here is to bring all the engineers of the different components, subsystems together in one room, in one facility, and they have to work for 1 week or 2 weeks on a mission plan. So they try to specify what the mission goal is and the system should look like. And this is how we can also support with software. The core idea here is really to bring the people together. It's a human, it's not the system, it is not software. But in the background, we have the software collecting all the information of these interactive negotiation between the subsystem and engineers, and to collect the data for a conceptual data model. So that's the idea, and this is implemented in our system called virtual satellite. We consider the virtual satellite nowadays also as some kind of a digital twin, but we do not have a physical twin here. Therefore, we follow the definition by Greaves and call it a digital twin prototype. So we create the prototype of a digital twin with our virtual satellite. And the idea is now to go into an interactive modeling. So the people can they do not have to sit only at their desktop and to type in their parameters in a data model. They can also go into Splinter meetings, and then they can use our virtual satellite, which uses the collected data and to create a visualization of a very first design draft. So as you can see here on the right-hand side, and then they can start to change in that kind of a virtual Splinter meeting. They can change some parameters, and they can discuss the new design after the changes. So this is how we call what we call visual engineering. Yeah. With some additional right management integrated, the engineers for subcomponents are only able to change those subcomponents they are responsible for. So, and this is a pretty sufficient approach, because you see immediately what you get. And you can see also the other engineers, and this really leverages the communication between the different subcomponent engineers. Yeah, sure. So, and with integrated AI methods, you can support this work even further. Right now, we try to integrate large language models to record the communication, to create documents of the session. And the idea is also to use it to come up with recommendation for requirements. So requirements is one of the big burden, especially in the early phases. All right, here you can see a video, two videos, by the way, of that kind of an extended reality collaboration session. On the right, on the left-hand side, you see the engineers, how they interact, but you cannot see the model at all, because this is just enabled by the HoloLenses they wear. On the right-hand side, you see the first-person view of one of the engineers, and then you can see the model presented in the room, and it is synchronized. So all the people can see, or they see the same model at the same place. And when one engineer is modifying something, the modification is automatically synchronized. So, and this is a pretty nice approach to speed up the design questions. All right. We are not only in the first, in the early phases, we cover the whole development life cycle of spacecraft. And at a certain point, when it comes to the integration, the system has to be assembled and software has to be integrated. And we are the Institute of Software Technology, and therefore our main interest is software. We can also use the models, the model-based approaches for model-driven generation of software. It is not just the design software we are developing, but also the flight software for space missions. By the way, that's the responsibility of a second department. I'm more on the, let me say, software aspects, and the second department is really on the flight software and to see how they can be integrated. A very successful mission. It was a mission with a sounding rocket, is depicted on the right-hand side. This is called Marius. And here we developed domain-specific languages. And the idea for that was we do not know what the, in this case, the scientists want to carry out with the sounding rocket experiment. So they want to switch on and off lasers. This was the case here, to create a Bose-Einstein condensate. So this was pretty complicated already for the engineers, but the scientists are not software engineers. So they do not know how to develop a driver for such a kind of a system. And therefore, we developed domain-specific languages, not only textual DSLs, but also graphical DSLs, so that they could now more or less design but write code. Yeah, so the software they need to carry out the experiment. So the DSLs has been forwarded to a model, and the model then could be used to generate the source code for the drivers, for the experiments. It was also used to create the documents and the unit tests for the software, which has to be carried out later on the experiment. So you see, this is the overall game, let me say. So on the lower part, you see again the European Corporation for Space Standardization, how it looks like. So we have a development life cycle, we have an operation life cycle. We are mainly on the development life cycle. Here we have the phases and a lot of reviews. So the boxes here with the arrows are all foreseen reviews for the standard. And we want to develop software to support that. So, and this is the upper row. Here you can see the software engineering. And we subdivided that more in a phase for design. We have a phase for assembly. So AIT stands for Assembly Integration Test. AIV is Assembly Integration and Verification. Yeah, and then it comes to the operation and maintenance. So we have a part for the onboard software. That's bright green, and we have the dark green, which is the software supporting generating software, and to analyze and simulate something and to control additional stuff. The on-ground software, by the way, is also standardized. So there's a further standard is called EGS-CC, which is the European software for on-ground control. And this is a software communicating with a satellite, for instance, so with the onboard software. Yeah. So, but we want to address the uppermost arrow for software to go ahead and to support simulation and analysis. All right. So, and here digital twins comes now into play. Okay, so and I found a very nice paper from Kombemal and others. So I think 23 co-authors are on the list on the paper, and they described a framework which is called Models and Data, a MODA framework. I think this is pretty good paper as a guideline for our own development. It is a model which also aims at support for the whole life cycle of a system. So should fit for that what I have in mind. It considers systems which are pretty software intensive. So, okay, if we are on software, it is software at all and therefore very intensive. We have with spacecraft, we have nowadays also cyber physical systems. Software becomes more and more important in such systems. And social technical systems, okay, we also want to integrate humans, so humans in the loop in the overall system, in the overall development. And as the next step is, the next important point is that it is very data-centric. So on the diagram on the right-hand side, you can see such kind of a physical system has get in some sensor data. So the environment creates a lot of data needed by the system. The system then creates some output data, actuator data, or measured data. The environment is measured, the system, the performance of the system is measured, and therefore a lot of data is generated and can now be used to describe the model. So here you see some internal models which describes the system. So more or less some kind of a shadow of the physical system. And here you see then a descriptive model describing what we have at the moment. This data can be used for predictive models, which analyze that and create some predictions, some decisions, and the prescriptive model can then be used to take the results of the predictive model and to create, for instance, updated software. For satellite missions, we can upload software. We can compile the software on ground, and then we can upload via telecommanding telemetry to the satellite to fix bugs. That is also possible in the space domain. Okay, now this is a nice framework, and we've taken that as a blueprint, let me say. Yeah. So, and how can we now design our system? Yeah, some ideas are already published in this paper. On the right-hand side, you can see what their ideas are when it comes to software development. So we are more on the system development, but it is quite of interest to see the software development can also be covered by the MODA framework. They depicted 3 examples. The first on the right bottom side, it's the test-driven development. And you can see It comes without a descriptive and predictive model. It's just a prescriptive model, has data and creates then the software. So also the agile approach or extreme programming approach comes without a predictive model. And the waterfall model comes also without any predictive models. When it comes to the system development, they presented two examples. The first one was about an airplane command and control system depicted on the bottom left side. Also, that is without any predictive models. But when it comes to a digital twin application, all three models, the descriptive, predictive, and the prescriptive model, have been presented here. So you see, the MODA framework does not aim at digital twin only, but tries to be very generic. But we like that approach to go ahead and to take now that MODA model to conceptualize digital twins for different purposes for spacecraft. We did not develop that by our own. It was somehow a predecessor publication of these authors, depicted here on the right-hand side by Eramo et al. They used the MODA model and now they conceptualized digital twins, so as a blueprint more or less. Here we have the actual system in a system environment, creating data which is then stored in a digital shadow. And the digital shadow is a raw data more or less, and in the supports the descriptive model, as you can see in the diagram. Here you can find description of the system. Also, our conceptual data model would be defined here. And can also have some information about past aspects that could be also stored here. Yeah. Then this descriptive model can feed the predictive model, where we can carry out analysis, simulation, machine learning for decision making. And then the prescriptive model is that model in our digital twin concept, which deploys actions to the actual system. So this is what we want to take as well for our spacecraft life cycle, as depicted here. So at the first, we have the design phase without any physical twin, only our digital twin prototype with our CAF session as an example. Then we go ahead to the manufacturing. Here we have this assembly integration test. An example here is the sampling of a wing to a fuselage of a drone. Then we can go ahead with maintenance, also in the space domain. So we cannot bring the satellite to the garage to repair it. But there are ongoing activities which is called on-orbit servicing, so that we can approach with a service satellite. We can approach a damaged satellite to carry out some repair. So on the right-hand side, you can see an example how it looks like when we use extended reality to incorporate that in such kind of an on-orbit servicing. And the operation, if we have a rover on Mars, for sure, we can also use that kind of virtual environments to plan the operation, to control the operation. All right, and this brings me to the virtual reality continuum. So let me see how much, what time it is. There's some minutes left. So virtual reality continuum addresses exactly that, what is in that term. So we have reality, or could be a satellite, so it's assembled. So, and now we want to get some additional information of the satellite, so we can blend in some computer graphics information over the physical object. Then we have augmented reality. It can become more complex, 3D immersed virtual objects somehow overlapped or hidden by the physical object. Then we are in the augmented virtuality up to that point that we completely immerse in a virtual reality environment. As you can see on the right-hand side, here you can see a person, an engineer in a so-called exoskeleton controlling the service robot at a damaged satellite and can now control the operation directly via a video stream. Yeah, and this can be planned and also supported by complete virtual representation of that kind of environment. So again, virtual virtuality continuum is depicted as here. So you can start with a virtual satellite in an engineering workspace. You have the full access to your conceptual data model. You can change your parameters, and you can start analyzing what you've collected with some visualization of diagrams. You can change the perspectives, and you can therefore dig deeper into that what you've designed. Then you can go ahead from your desktop to the mixed reality. So mixed reality is virtual reality, and then you can blend in more information. You can overlap information. You can interact with virtual and also with the physical objects. Yeah, and the final step is then you can move on, take your data with you, with your system with you, and then you can analyze something what is only possible in a pure or full immersive and virtual environment. If you, for instance, want to stand on Mars, what is depicted on the right-hand side. Okay, so but we have some challenges using digital twins in augmented reality applications. So in the first place, it is collaboration. So if we are not alone, not just one engineer, how can we now interact with the data? How can we communicate with each other? And the whole story becomes much more complicated if we have people not in the same room. So often engineers are very skilled experts, and therefore we do not have so many experts worldwide. And then it makes sense also to have some kind of a video conference or video session, so that the experts can come together in virtual rooms and to think about designs or support assembling or something like that. Yeah. The next point is when we want to map virtual objects to a physical object, the location of such kind of information has to be very stable. Yeah. So if you have some jittering or the data is not exactly joined to the parts or so, this creates issues, and at the end, the engineers would not accept such kind of approach. Yeah. And the third part is, how do we interact at all with the data? So, I mean, at the desktop, we know we have the mouse, we have a keyboard, we know how to do that. We know that for decades. But if you want to integrate very complex tasks in such kind of a mixed reality environment, it is not clear. It's how intuitive interaction tasks could look like. And they are pretty dependent on the task you have in mind. For instance, if we are not talking about a system, but for instance, about smart cities, here we can also bring in digital twins, and here we can also interact with. How can we do that? But if we can really bring that to life, we can then use such kind of environments to guide, for instance, relief forces when it comes to some kind of disasters, wildfires, or an accident in a city or so. Yeah. Here also we can annotate and augment models. And this can be taken also as some kind of documentation of what we've carried out. And then it can be stored also with the digital twin. And the third point, which is also very important, is this can be a next step forward to integrate citizens in such kind of environment. So if we have such kind of a system, for instance, in a car, and we can call, when it comes to an accident, we can call some forces to the hospital or whatever, to bring some forces to help to relieve here the situation. We can create nice distributed systems, and actually this is what DLR is on as well. All right. So now the third part is about visual data exploration. Yeah. The data is stored in the digital twin, and it is not just to visualize shapes of a satellite or so, parts of that. It is also abstract data, and therefore it is important to have also visual analytics tools to go deeper. We did that for the analysis of for the corona disease, as you can see on the right-hand side, and visual analytics helps us with linking the data together. If you change some views, all the other views are updated. And therefore, you have always a consistent presentation of the data, which helps you not just to look at diagrams, static dashboards, but to interact with the data, yeah, to dive in and to explore, and maybe to identify new findings you had no idea about. Yeah. So this is called linking and brushing. You can mark some parts, and then you get the linked presentation and other diagrams. We can also carry out focus and context approaches. But integrating also predictive models in such kind of visual analytics approach also helps to analyze uncertainties with the data. And I think that's a really big advantage of also machine learning, ensemble simulations, to bring everything together and then to go visually on that to analyze what you have and to compare different analyses. All right. We need also the environment. So we need also a visualization for environments. For such kind of visualization, we can bring in, for instance, when it comes to simulation of satellites on orbits. If you want to see if you want to approach a damaged satellite, it is important to get an exact pose of the damaged satellite and the surface satellite. And this can be simulated in advance. But then we need the exact environment, how the light condition is, where the stars are, and so on and so on. And therefore, we developed also a tool which nowadays offers the whole solar system in real time in highest precision, because it relies on OGC servers, which provides the highest resolution of planetary data you can imagine. But we support also other information, but maps, for instance, multispectral data, cloud, point clouds, and so on can be processed, so that we have the opportunity also to dig deep into big data. Yeah, that's also linked to virtual reality support. And if you're interested in that kind of tools, most of our tools are open source, and you can download them to use for your own purpose. All right. Simulation is a big topic here. It's not just measured data. We can incorporate also weather simulation. We can support climate research. And we had also some research on mental convection. And everything is visualized, integrated in our Cosmos Scout system. Simulation is very important, again, if you come back to systems engineering, when it comes to certification and qualification. And what I mean here is we can use a simulation to support certification and qualification by analysis. So therefore, we have to identify the math behind or to describe the reality, and then that can be used to create some simulation models which can then be carried out. Very important here is that the simulations themselves are somehow embedded in the space we measured with experiments. So the reality is sampled by experiments, and the virtual environment, the virtual world more or less, is then in that state space, so that we can use the simulation now to certify different alternative configuration of a system. Yeah, and we want to use now these approaches of simulations also to visualize it in an overall environment, and also with visual analytics, that we can then dig deeper into some aspects of the model validation. So in former days, they came up with a test pyramid, so everything relied on experiments, but we want to shift that more and more to the virtual world, that simulation can replace more and more very expensive experiments. And again, here, I think visualization, visual engineering can support the virtual certification as well. All right, so I'm quite late already. This is just an example we've implemented successfully for maintenance. So we have an engineer, you can see on the top image with a real air brake, and now investigating an impact in that shape. And if there are some unknown problems, if the question pops up, if this system has to be replaced or can be still used, the engineer can call the provider. It's the picture, picture here on the lower right side, and then they can collaborate. The collaboration can be supported by some kind of avatars, but here the avatars are not like, from avatars from the film or from computer games. It's just the eye gaze, what is depicted here, and then you have some kind of awareness what the colleague is looking to, so that you can then communicate with him. But again, all the visualization has to be synchronized, so that the overall distributed collaboration is supported in a good way. All right, this is a video to show how it looks like. This was on a fair. I will skip the video because it's quite long, 5 minutes, but it showed all the details. And let me jump to the last chapter of my presentation. It is about the engineering metaverse at all itself. And I always say, okay, the engineering metaverse addresses any data, anywhere, anytime. So, and this is what I want to integrate, also to keep the digital twin in mind. But I do not want, I want to get rid of the desktop application or some tools stored on some workstation and they're communicating via network. I think the solution here is cloud computing. So I've presented already in the project we've been on, the Kubernetes project, which aimed exactly at that. But we think that we have to think more in services. So, and this is the idea how we want to create different levels, starting with the infrastructure as a service, where we have container services, orchestration services, and so on. where we also have some layers for communication with networks and so on. Also, a back-end rendering service is foreseen. Then we have the next layer, which is a platform as a service. Yeah? Here you can see the virtual satellite. Also here, we do not want to develop everything from scratch again, but we rely on already good established tools and standards like the Django service. Here we want to integrate that on that level. We need also some identity services. So we have different users. They have to be identified. The users are identified in their context. So they are in a certain environment. If they're in another environment, maybe their representation is different and the tools they have are different. So therefore, identity services and location services are very important. And the topmost layer, you see software as a service. Here again, we have a virtual satellite for the concurrent engineering facility, a version for the integration, for the assembly integration and test. We have the use cases I've presented already here. And on the right-hand side, you see we want to integrate mocks for the digital twins models for the descriptive service, prescriptive service, and the predictive service. Visualization and data analysis on the right-hand side. So, and this is now the overwhelming last slide. You can see we are just at the beginning. This is some kind of a technology stack. We want to, there are plenty of different aspects. Virtual certification is depicted here, but we also have to address fast networks. So how to integrate 6G, the upcoming network standard. What kind of other scene graph APIs are available so that we can create scenes and these metaverse environments. Object recognition is an example. Multimodal environment, so it's not just visualization, but also haptics, sound, everything has to be integrated. Then we come to collaboration on the left-hand side, and system analysis, where we have the ontologies, the large language models, deep neural networks, and so on. And the top layer is then the human, let me say, the reality, virtuality continuum with our virtual environments. With IoTs, how can devices communicate with each other? How can they be integrated in the overall collaboration environment? You see, we are just at the beginning. A lot of challenges are identified, and I hope with the discussion with you, we can get a more mature path to a success for spacecraft. Yeah, thank you very much for your listening.
Thank you, Andreas, very much. I will stop the recording for now.